Hello everybody, this is video 10.4 on triangles, quadrilaterals, and other polygons. This is obviously building on the stuff we've looked at already involving triangles and introduces a little bit more in-depth material on quadrilaterals like rectangles and squares that we've looked at already. So let's get started. So this is review. These are not new terms here. We have the idea of a plane shape or a planar shape, and so this is an object that lies in a plane. So we can think of it as a flat object. So it has potentially length and width, for example, but would not have any height or thickness. So if you could draw it on a piece of paper, where the paper is sort of acting like a finite part of that plane, because remember the plane keeps going in the two different directions that are the two dimensions of the plane. Uh, so we could draw a triangle, we could draw a circle, we could draw a square on a piece of paper. Those are all planar shapes, but we can't draw a sphere on a piece of paper, at least not very convincingly. So those would not be planar shapes. We'll look at those a little bit, but those would be examples of spatial shapes. Those exist in space. So we could think of a circle as being a plane shape. Now, I put typically there because remember, a circle could still exist in a space. Um, so a circle could still be in three dimensions, um, but a sphere is a spatial shape. It's in three dimensions, but we couldn't really put it into two dimensions. So, um, yeah, the contrast between these. So two-dimensional, again, having length and width, but not height or thickness. Or realistically, you could pick any two of those dimensions, and it wouldn't have the third. So you could say a two-dimensional object is one that has length and height, but doesn't have width, and so it would still work. So it's going to be continuing in two of those directions, having two of those dimensions, but just lacking that third one. We've talked about this before, so hopefully this much is review. So when we think about how we classify shapes, the first thing we do when we're kiddos is we look at certain very basic characteristics of a shape. So the number of sides, we begin to recognize a triangle is different from a square because a triangle has three sides and a square has four sides. The number of angles, and the number of angles is typically related to the number of sides. So a triangle has three sides and three angles. And when we're saying angles, and the book refers to angles, we're talking about the interior angles, not the exterior angles of the triangle. So let me draw a picture of this real quick. So when we're talking about the angles, so if you remember earlier, we talked about this as being an internal angle, but then this red angle out here being an external angle. So this is external, and then this angle here would be internal because it's inside the shape. So we looked at this before when we saw that this external angle is going to be equal to the sum of these angles over here. So yeah, when we're talking about angles here, we're talking about internal angles. The types of the angles, whether or not we're talking about acute, obtuse, or right angles, and then also the symmetries. So even within triangles, we might recognize that some triangles have more symmetry than others. Some triangles may have uh, one main symmetry, might have three lines of symmetry. So a couple of different ways of characterizing these. We're going to take these characteristics and these classifications and look at them a lot more today and start to create sort of a structural way of thinking about how these objects are all related. So we're going to start with the most broad form of four-sided figures, which is a quadrilateral. So anything that has four sides and is closed and is formed by straight lines and then does not have sides which cross over each other. And this is a little bit of a weird point. This is kind of optional, so if you find this confusing, then forget I talked about it. The book mentions that the sides can't cross each other. That's not entirely correct. If the sides cross over each other, then you still get a quadrilateral. It's just called a complex quadrilateral. And so really what we were looking at are what we would call simple quadrilaterals. And they'll make a lot of the things that we're talking about make sense. So we'll eventually look at area formulas of quadrilaterals. And if they cross over each other, I mean, finding the area of this rectangle is pretty simple. Finding the area of this rectangle is a little bit more complex. So that's why we're not really going to be talking about these complex quadrilaterals right now, because a lot of what we're going to be doing with this won't apply to those. But technically, they're still quadrilaterals. What do we mean by closed? Well, by closed, we mean that the figure should form a closed area. So this would not be closed because we can see that there's not an inside and an outside. It's all sort of one thing. So this is not closed. And then formed by straight lines should be fairly obvious. We can't have anything where, if we have, say, a rectangle, but it's like this, yeah, that's not going to work. So this is closed. It definitely forms an inside and an outside. We can see this is the interior of the shape, but the fact that this is a curved line here means that it doesn't really form a quadrilateral. We can still work with shapes like this. I mean, it still has some purpose and utility, but it's just nothing we're going to look at right now in this section. These shapes all down here in the corner, these are all quadrilaterals. This one looks like it wouldn't be, but it is. It definitely works. You can see that it is closed. The blue area is inside, and then we can see there's an outside to it. It's formed by straight lines, yeah, and none of the lines cross over each other. Now, if we were going to extend these line segments into lines, then they might cross over each other. But as they are now, this totally works. So this is called a concave. In case you're curious, it's sort of optional. But this is called a concave quadrilateral because it forms this little dent in here. And there's a more sort of there's a better definition than that, but it's sort of beyond the scope of this class, so we won't get into it. But this is kind of a tricky one. It seems like it wouldn't be a quadrilateral, but it absolutely is. So now let's look at some specific types of quadrilaterals. And I'm going to assume that most of these, if not all of these, are shapes that you've at least heard of. Whether or not you remember a whole lot about them or not, we'll see. But hopefully everyone in this class has heard of a rectangle before. So a square. A square is a quadrilateral with 4 right angles and all sides having the same length. Now, when we say all sides having the same length, this is the same thing as just calling this congruent. So we could say having 4 right angles and all sides congruent, and it would mean the same thing. So that's a square. Now, a rectangle is a quadrilateral with 4 right angles. So as soon as we have 4 right angles, that's sufficient to make it a rectangle. A rhombus is a quadrilateral where all the sides have the same length. We also have a parallelogram, which is a quadrilateral where the opposite sides are parallel. So the shape that a lot of people sort of have in their mind for a parallelogram looks a lot like this, where you can see that this side and this side form a parallel pair, and then this side and this side form a parallel pair also. So this is what we mean by a parallelogram. Opposite sides are parallel. So these are opposite each other, and then these are opposite each other. The last one is a trapezoid, and this is a little sticky because depending on which textbook you're using, you may see different definitions. Some books say that a trapezoid has at least 1 pair of opposite sides. Now, if this is the case, then every parallelogram would also be a trapezoid. So this would include parallelograms. Now, if it's exactly 1 pair of opposite sides parallel, then this does not include parallelograms. You would think that there would be like one definition for it, and I'm not entirely sure why there's not. But the reality is there's not. And so this question of whether or not a parallelogram is a trapezoid or not will sort of depend on the way it's defined in your book. So typically when we see a trapezoid, it looks something like this. And so a lot of times you'll see the non-parallel sides, these are drawn almost like exaggerated to make sure that they're not parallel. And then we've got this side up here and this side down here. These are the opposite parallel sides. So this works for either definitions because this is either exactly one pair or at least one pair. If it includes two, then we include parallelograms. If your book doesn't include two, then we wouldn't include parallelograms. One of the things that's kind of tricky about these definitions is that these are not the only definitions, and I've kind of copied the definitions that are in the book. Um, so So you may see different forms of these definitions depending on where you look. And so, for example, you may see this definition like we have down here that a square is a rectangle with adjacent sides congruent. And so that's a definition for a square. It's based on knowing what a rectangle is, and it uses this idea of adjacent sides being congruent rather than anything about opposite sides. So it's a slightly different version, but it means the same thing. So um, depending on which book you use, depending on where you look on the internet, depending on who you ask for help or ask questions, you may see different definitions, but they should all point to the same type of object. Just know that there's different ways of defining these objects. So does this mean that a square is also a rectangle? Well, yes, absolutely it is. And so you can see here in this chart, we've got our most basic shape here, this quadrilateral. And then from this, and now this chart assumes that a trapezoid is exactly one pair of parallel sides. Because we can see that the trapezoid and the parallelogram are separate from each other. So a rectangle is going to have these four right angles. And then the rhombus is going to have these four sides all congruent. And so if I combine those characteristics together, then I have the four right angles of the rectangle plus the four congruent sides of the rhombus. And so a rectangle plus a rhombus makes a square. Uh, so you can also see that a square is not only a rectangle, it's also a rhombus, it's also a parallelogram, and then depending on how we define this trapezoid, it might even be considered a trapezoid if we're using the at least one definition of a trapezoid. So we can see that these are sort of included in these categories. That anytime I have a rectangle, I also have a parallelogram. Anytime I have a rhombus, I also have a parallelogram. Anytime I have any of these, I have a quadrilateral. So it's not really important that you memorize this chart. It's probably not the best use of your mental effort. But if you understand what all of these definitions are and how all these shapes are defined, then it should make some degree of sense how all these fit together. The key is in not thinking about these as being separate objects, but rather objects that sort of overlap with each other. So once you sort of come to terms with the idea that every square is a rectangle, but not every rectangle is a square, then making sense of this chart should be a little bit easier. So now let's leave quadrilaterals for a moment and talk about triangles. And so really this is almost the exact same definition that we had earlier for quadrilaterals, except that we've got three-sided figure instead of four-sided figure. We also can get rid of the part about the lines crossing over each other, because that's a lot harder to manage with a triangle. And so we have an example here, these things all as triangles, and then we have these shapes on here which are not triangles. So you can see that this is not a triangle because this has four sides. We also have this shape over here, which is not a triangle because it's not closed. So this breaks this closed part here because we can see there's an opening here, an opening here, and an opening here. So there's no inside or outside. This is all one sort of region here. And then we can see this is not a triangle because this is not a straight line. So we've got this side here formed by this curvy line. So this does not form a triangle. So almost identical to what we talked about with quadrilaterals, the same things apply for triangles. Just like with quadrilaterals, we have different types of triangles that we can define as well. And these are all different types of triangles except for this one, which is a part of the triangle. So we've got a right triangle, which is a triangle which contains a right angle. And I'll leave this as sort of an open question as to why it can't have two or three right angles. It's only going to have one right angle. And so this triangle, a lot of times we'll see it. It's sort of drawn like this, and it's got the little right angle mark down here. Now, in any right triangle, we've got one side that's going to be longer than the other two sides. And so in this case, you can see this is the longest side. And it's also going to be the side that's across from the right angle. So it's opposite from that right angle. And this side is called the hypotenuse. So this is the only term here, which is not a type of triangle, but is a characteristic of a right triangle. If you have a triangle that's not a right triangle, we wouldn't call the longest side a hypotenuse. That's strictly for something that's a right triangle. So if I were to draw a triangle like this, we wouldn't really call this, and I should make an effort to make this a closed figure. I wouldn't call this the hypotenuse because this is not shown as being a right triangle. So even though it's the longest side, like I said, it's not a hypotenuse. We also have the equilateral triangle, which is a triangle where all the sides are the same length. And so a lot of times we'll see this drawn like this. Ooh, what happened there? Let's try that again. So we've got three, oh my goodness, what is going on? So one more time here. There we go. And so for an equilateral triangle, a lot of times we'll see these little marks like this. And so again, this shows that the length of this side is the same as the length of this side is the same as the length of this side. So this is what we show as an equilateral triangle. An isosceles triangle is very similar, but it has at least two sides that are the same length. And so something like this would be an isosceles triangle. And we'll put our two tick marks here to show that this side is the same length as this side. Now, you may notice that this at least means that every equilateral triangle would also be an isosceles triangle. If you have three, then you have at least two. I've seen this described before where people have contended that an isosceles triangle is exactly two sides of the same length. You don't see that as much as the difference in trapezoids, but you may see that come up as well. Although typically you'll see it be at least two sides. An acute triangle is one where all the angles are acute angles. So remember that means that all the angles are less than 90 degrees. And so this equilateral triangle would also be an acute triangle because all these angles would be 60 degrees inside this triangle. As opposed to an obtuse triangle where you have an obtuse angle inside the triangle. So I've tried to draw this as being an obtuse triangle here. This angle is meant to be greater than 90 degrees. And again, I'll leave this as an open question why you can't have two or more obtuse angles inside of a triangle. Just like with quadrilaterals, a lot of these categories overlap. We can have an isosceles right triangle, for example. So those exist. That's the thing. So these are categories down here about angles. This is a category about angles. These categories here, these two are about sides. And so you can have something that is about sides and about angles at the same time. So you could have, like I said, an isosceles right triangle. Now, not all of these things work because you can't have an equilateral right triangle. That doesn't exist. And again, I'll leave that for you to figure out why that doesn't happen. But these categories are not exclusive of each other necessarily. So you have to kind of think about whether or not that is possible. You could have, like I said, we had the acute equilateral triangle there. So we could define it as both. Typically, if you call it equilateral, you wouldn't say the acute part, but you could, and you wouldn't be incorrect if you did. We also have what's called a polygon, and this is now expanding this out. We've looked at three sides, we've looked at four sides, but now we're going to look at n sides, where n could be, pretty much any number greater than 2. This doesn't really work all that well if n equals, 0 or 1 or 2. So typically n is going to be at least 3. So n is greater than 2 or greater than equal to 3, however you want to think about it. And so you can see it's a very similar definition to what we've had before. This is the generic name for any n-sided figure. Again, it needs to be closed, straight lines, and the lines should not cross each other. And again, if they do, then it forms a complex polygon, which again, we're not going to talk about in this class. It's a little bit beyond the scope of what we're doing here. A lot of these are names that you've heard of and know. We've already talked about triangles. We've already talked about quadrilaterals. If n equals 5, this is a pentagon. If n equals 6, this is a hexagon. 8, an octagon. One of my personal favorites. If it's 12, it's a dodecagon. It's kind of a fun one. And so on. And kids love learning these kind of like crazy names to some of these shapes. And so, the students will ask, well, what if it has 17 sides? What's that called? And so you can go Google it, go look it up and see what it's called. There's names for all of these, although certainly some are more common than others. But yeah, absolutely, this is what we refer to as a polygon. Now, we'll refer more to as polygons, but they're also sometimes called n-gons, which is a little bit weirder to say. So an n-gon is if we're saying any polygon with n sides. But generically, we'll just use polygon because it's a little bit easier to say and understand what's going on. Polygons can be what we call regular. And a regular polygon means that all of the sides are congruent and all of the angles are congruent. So we've already looked at two regular polygons. So an example of this would be a square, which is our regular quadrilateral, and also our equilateral triangle. Those are both regular. And so there's a little chart here that shows some examples. This regular hexagon here, for example, we see that it has 6 sides. They're all the same length, and all the angles are meant to be the same as well. And then it contrasts to this, which is our irregular hexagon. And we can count 1, 2, 3, 4, 5, 6. So it has 6 sides. So it is a hexagon. And we can see that it's formed by straight lines. And we can also see that none of the lines cross over each other. So this is a hexagon. It's a simple hexagon, but it's not regular because not all the sides are the same length. We can see obviously this side and this side are not the same length. One's clearly longer than the other. So we know right away this is not regular. Now, I included this because when I was looking for a graphic to use for the slide, I found this, and well, there's an error because this is not a regular pentagon. I'm not sure who made this and why they put that there, but you can see clearly this and these two angles look like right angles, and this one might be a right angle, but this is clearly not a right angle, and neither is this. So all the angles look like they're not all the same, and the same here. Uh, these look like they're congruent to each other, but this one looks like it's a different length altogether. This does not look equilateral. So, just be careful looking online. I mean, this was one of the first things that came up when I did a Google image search for regular and irregular polygons. Over here, we've got regular shapes, and two of the three are wrong. So, I don't know, just be careful with that. Now, we also have this thing called a Venn diagram, which allows us to use shapes to show how things are related. Now, the book makes a very specific point to say uses ovals. And so I found two examples. One which doesn't use ovals, it uses circles. And then down here, sometimes we'll also see Venn diagrams that use squares and rectangles instead. Now, yes, most of the time we do see ovals of some form, but you know, I didn't like the fact that the book put that specific of a context to it. It doesn't have to be ovals; it could be anything. And so, if you've never seen one of these, what this shows us is how things relate. And so over here, this set are characteristics of an apple. So things that describe an apple. I didn't like how it just says apple. Like, I mean, what about an apple? So, to say, well, these are things that describe or are characteristics of. And then over here on this side, we've got things that describe a tomato. So describe a tomato. And so we can see inside we've got fruit, round, and smooth skinned. So this part in the middle is going to be both tomato and apple. These are things that are common to both tomatoes and apple. I don't understand why this doesn't say red in here, because when I think of a tomato and I think of an apple, I think of them being red. Although I guess a tomato and an apple could both be green, so maybe that's why that's not on the outside. But that's the first thing I think of. But they are both fruit. Um, whether or not you believe a tomato is a fruit or not, it is a fruit. Round, I suppose, is subject to some sort of debate there, because I mean, an apple has the little thing at the top and at the bottom. They're not perfect. Neither of them are really perfectly round. But smooth skinned, for the most part, that's true. Now over here on the right, we've got things that apply to an apple that don't apply to a tomato. So this is things that these are things that apply to an apple but not to a tomato. So if you open up an apple, typically it's white on the inside. And then over here, these are things that apply to a tomato that don't apply to an apple. And so when you open up a tomato, it's typically red on the inside. So we can separate these things out. Now, there's also on the outside here, there are things that would be neither. And so we could say green insides. And so this is neither a tomato nor an apple. It's neither of these. And so this region on the outside is typically also a region. And so we could also put out here vegetable. A tomato is not a vegetable, and neither is an apple. So this would be a characteristic that would be on the outside of these. So you can probably see where this is going. We can use these Venn diagrams to show relationships about quadrilaterals. And that's what this looks like. So this is an example, and again, you can do a Google search for quadrilateral Venn diagram, and about 1,000 of them come up. I tried to look for a funny example of a Venn diagram, and I did a little search for those, and almost none of them were appropriate to share in class. So I'll let you do that at your own risk. But we can see here how these are all related. And again, this is very similar to the diagram or the hierarchical tree that we had on an earlier slide. And so you can see here that squares are where rectangles and rhombuses sort of intersect. And you can also see that a square is contained inside of the parallelogram circle. And so we know that every square is not only a rhombus, but it's also a parallelogram, it's also a rectangle, and then everything is inside this big quadrilateral bubble. We can also see over here, because the trapezoid circle and the parallelogram circle, or those two sets, don't touch each other, then we know they're using the exactly one pair of parallel sides. They're using the exactly one definition for our trapezoid over here. So again, you don't need to memorize this. Hopefully, if you know and learn all the characteristics of these shapes, then being able to construct this diagram should follow pretty naturally. And that's your checkpoint question. So without looking at your notes or without looking at the slides, try to draw a Venn diagram that shows the relationship between rectangles and squares. So just start with those two and make sure you understand how those two are related. And then try to add in parallelograms and then rhombuses and quadrilaterals and trapezoids. Try to add these circles. Now, we haven't talked about some of the shapes that were on the previous diagrams. Like we didn't really talk about kites as shapes either. So you can kind of like leave those out. But see if you can construct the Venn diagram or the table from the earlier in the slides. See if you can construct those, and if you can, that's a pretty good indication that you know how all these things are related. And if not, look at the ones you got wrong. So why did you draw a certain way instead of the way that it was meant to be drawn? So if you have any questions about the Venn diagram or the hierarchical table or why you got wrong something you got wrong or any sort of misunderstanding about it, but as usual, bring those questions to class and we'll get them answered. All right, thanks.